Exercise 4 part A. Here you have a set X and on X you have a family of topologies tau alpha indexed by some set which is there in the background that is not being shown explicitly, but for each label alpha in that index set you have a topology tau alpha on X. We then have to show that the intersection of all the topologies is itself also a topology on X. The first condition for a topology is pretty simple to verify here, because each topology tau alpha contains the empty set as well as the set X. That means these things are elements in tau alpha for each alpha in whatever index set. So the intersection of all the tau alphas would also contain those two elements. So next we consider any arbitrary family U beta of elements in this intersection, and let U be the union of the elements in this family. Our aim is to show that this U also belongs to this intersection. Now for each index alpha, this of course is also a family of elements in tau alpha. What does it actually mean for this to be a family of elements in this? It just means that for each index beta, U beta belongs to this intersection as an element. So that means each such U beta belongs to each such tau alpha. But each tau alpha is a topology, and so the union of those U betas, all of which belong to tau alpha, would also be in tau alpha. That is U is the union, it will belong to tau alpha for each index alpha. And that's how U belongs to the intersection of all the tau alphas. And finally, we take two elements U1 and U2 in this intersection. Then U1 and U2 belongs to tau alpha for each index alpha. Because each tau alpha is a topology, so the intersection of U1 and U2 also belongs to each tau alpha, which means that the intersection belongs to the union of all the tau alphas. And from this fact that the intersection of any two elements in this set is again in the set, we can prove by a simple induction that the intersection of finitely many elements of this also belongs to this. And that is why, by definition, this is a topology on X. That is part A. Next, let us see part B. In part B also, again we have a family of topologies on X, tau alpha. Now we have to show that there is a unique smallest topology on X which contains all the tau alphas within it, and also a unique largest topology on X which itself is contained inside all the tau alphas. So we start the solution with this collection A. Let A be the collection of all objects tau such that tau is a topology on X and tau contains all the tau alphas within it. And then we consider the intersection of all the elements of A. But let's be a little careful here. Can we consider the intersection? See, when you consider an arbitrary intersection of a collection of sets, you may run into difficulty if the collection itself is empty. In that case, actually in this text, intersection has not been defined because there are some logical problems that arise. So whenever you consider an intersection like this, you have to first of all make sure that the collection whose elements you are intersecting, that is non-empty. Is it non-empty? Yes, it is non-empty. Can you give an example of a topology that belongs to this collection? Yes, that is the discrete topology on X. The discrete topology on X is actually nothing but the power set of X. It is a legitimate topology, we already know. And whatever the tau alphas are, the discrete topology contains all of them inside of it as subsets, simply because it has all the possible subsets. So yes, the discrete topology is a legitimate element of this collection, making it non-empty and allowing us to consider this intersection. and by part A, this intersection is a topology because it's it's the intersection of some topologies on X. And also, it is clear that it should be the smallest topology on X containing all the tau alphas. Why though? That is because, say you consider any element of this A, any topology tau which contains all the tau alphas, then obviously the intersection of all the tau alphas would also be contained in that tau. And in that sense, it is really indeed it's the smallest topology on X which contains all the tau alphas. Any other topology would contain this one inside of it. In that sense, it's the smallest. And then of course we have that largest one also. The solution is not over. And this second part is quite easy. The largest topology on X contained inside each tau alpha is the intersection of all the tau alphas. By part A, again, just like that one, this one is also a topology on X. And why it's the largest one to be contained in each tau alpha, that part I leave to you to figure out. And next we have part C also. In part C, this concrete three elements that X is given consisting of A, B and C. These are three distinct objects. And we are considering the following two topologies on X, tau 1 and tau 2. You can see tau 1 consists of this singleton set A and this pair set A, B. Besides of course having those two things, they are always there. Similarly, tau 2 contains this A and B, C. We have to find the smallest topology on X containing tau 1 and tau 2 and the largest one contained inside tau 1 and tau 2. So that means it's part B, but in this specific case. The smallest topology containing both tau 1 and tau 2 is this. Because I needed the space, I had to erase tau 1 and tau 2, so I again wrote them here because we need to see them to be able to figure out how we are getting this. So what do we need here? We need a topology on X that should contain both tau 1 and tau 2 inside of it, which means that all these open sets in tau 1 and all the open sets in tau 2 need to be elements in this topology. So first we gather the sets. The empty set and X of course have to be there. Besides them, we should have this singleton set A, so we write that here. We also take A, B and B, C. And then we see what else do we need. That is, we cannot just simply keep that collection itself and call it a topology. It needs to be a topology. And when you go through the conditions for a collection to be a topology, you see that the extra set that you need is this. Why? Well, if you take intersections of finitely many elements from a collection, that intersection should also belong to that collection. Now, if you take in particular the intersection of these two sets, you get the singleton set B, so that should be there. So you include that in the collection and then you see whether that makes it a topology. Yes, it turns out that this is a topology. So we did the bare minimum that we had to do to turn it into a topology, and still it contains both of these things. And that is how it's the smallest topology on X containing both tau 1 and tau 2. And next we go for that largest one. So that largest one is just this by part B, and which is this. The only common elements to tau 1 and tau 2, both of them are these three sets. So they form this topology. And that's just it. Let me just end this short video here itself. I think there are two more even numbered exercises still left for us in this exercise set to do. One of which, number 6, we have already actually done. It is about comparing the K topology and lower limit topology, I think, if I am remembering correctly, or to show that actually they are not comparable, which if you remember we already did there before. So that means we are left with only one exercise. that we will solve next week. So see you next week with number 8 and its solution. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.